Welcome back to Earth and Life Science subject. Still, this is your Sir Siloso, your lecturer for today's session. Last week, we discussed the different processes happening beneath and on the surface of the Earth. And those are endogenic and exogenic processes. All these geologic processes continue to change the appearance of the Earth. So the question is, how did the Earth look before? That's why for this week, we're going to talk about the deformation of the Earth's crust. When I say deformation, it is the process by which the crust is deformed along tectonic plate margins. Deformation in general produces a variety of geologic structures such as folds, faults, joints, and foliation. We all know that the geosphere of the Earth is subdivided into three main layers: the core, mantle, and the crust. The crust is subdivided into two main types, the oceanic and the continental crust. The thin oceanic crust that underlies the ocean basins, and the thicker continental crust that underlies the continents. If we're going to compare these two types of crust in terms of density, the oceanic crust is denser compared to continental crust. The low density of the thick continental crust allows it to float in high relief on the much higher density mantle below the Earth's surface. The ground beneath our feet is always moving. We don't feel this often, but we can see the results of the movement almost everywhere. The Earth's crust is what moves, our planet's outer shell. It is not one piece, but instead is made of individual puzzle pieces, plates. They were all part of the continent that drifted apart over 200 million years ago. Since then, it hasn't stopped moving. This is called now as tectonics. In 1912, geophysicist Alfred Wegener developed the concept and hypothesized the continental drift theory. He claimed that there used to be only one supergiant landmass where all the continents came from, and this supercontinent was named as Pangea. Continental drift theory states that all continents were once joined together in a single massive landmass and have since drifted apart. Over time, this continent broke apart into two huge landmasses, and these two landmasses moved away from each other. The two giant continents were Laurasia, which comprised the continents in the present-day Northern Hemisphere, and the Gondwana land, also known as Gondwana, which comprised the continents in the present-day Southern Hemisphere. The separation continued until we have the continents that we can see on the map today. Did you know that Wegener's theory was rejected by scientists because he could not explain what force pushes or pulls the continents? That's why Wegener proceeded by providing strong pieces of evidence of his continental drift theory. He searched and found three main pieces of evidence: the geologic, fossil, and climate. The first one is geologic. Those are evidences in the layers of rocks across continents. The first piece of evidence is simply the observation that the continents appear together. As simple as that. The coastline of the continents appeared to fit together like the piece of a puzzle. If you look at the mountain ranges in the northeastern United States and the mountain ranges in the northern Europe, they match up perfectly. And it means that they are made up of same type of rock and same age of rock. Now, of course anything is possible, and the same rocks could have formed in two different locations at the same time. But geologically, that's unlikely. A better explanation is that these mountains were once connected, and as the continents moved, they tore them into two. And that is the first piece of evidence found by Wegener, and that is under Geologic. The next one is fossil. Those are evidences in the places certain fossils are found. The geologic evidence is not enough. That's why Wegener went back to the drawing board. He dug through files of books in libraries and became quite interested in fossils and other evidence of prehistoric life. Fossils are any trace of an ancient organism that has been preserved in rocks. In fact, Wegener came particularly interested with the mesosaurs. Mesosaurs are reptiles that live only in shallow fresh water. What's interesting though is that there's only two places in the world where we find fossils of this freshwater creature. One place is the eastern coast of South America, and the other is the western coast of Africa. Wegener said is that while the Mesosaurs roamed the land, Africa and South America were connected and they were able to freely walk across the land masses. And then after going extinct, the land masses were torn apart and separated, carrying some of the fossils to what would become South America and some to what would become Africa. Interestingly, Wegener looked into this and found that there are other organisms that lived in the past had similar fossil distributions. Cynonatheus, Distrosaurus, and Dosopteris, which is a fern-like plant that lived over 250 million years ago and was found in Africa, South America, Australia, India, and Antarctica. So that's the second evidence of Wegener, and that is under fossil. The last one is climate, the evidence in the changing climates during the past. Again, Wegener returned to the library and he began to look the past climate data, meaning he looked at the evidence of cold and warm weather in the different parts of the world, and he found something fascinating. He first looked at the glaciers. Glaciers are giant rivers of ice that move slowly across the Earth's surface. And of course, glaciers have to be found in the cold parts of Earth. Today, they were restricted to only the highest mountain tops and of course the north and south poles of the Earth. Something interesting about glaciers is that they move. And when they move over the rock beneath, they leave evidence in the form of scratches that we call glacial striations. If you look in the map, if you look in the present day, tropical rainforests of South America and Africa, you will find glacial stations. Here in these two regions, you find the scratches in the bedrock. Now, if you think about that, how could there be glaciers in the tropical rainforests unless it wasn't always a tropical rainforest? This suggests that these continents were not always in their warm equatorial regions like they are now. They were once down near the South Pole where it could have been cold enough to have glaciers, and they have since drifted apart. So that's the last evidence found by Wegener, and that is under climate. Did you know that India was once in the southern hemisphere connected to Antarctica? Did you know that North America was once surrounded by warm tropical seas? Did you know that Africa was once covered by glaciers, which were kilometers in thickness? And did you know that Sahara Desert was once a tropical rainforest? Wegener's theory initially did not gain acceptance from the scientific community because he could not explain why the continents moved. He just asserted that continents had been pulled apart by Earth's rotational force and some astronomical influences. Hence, his theory was given little interest that time. Sadly, he died in Greenland on an expedition. At the time of his death, no one believed his hypothesis. Technology developed during the 1940s changed all of that. In the 1940s, during an initial survey for ocean floor mapping and other geological explorations, certain findings led to the discovery of more accurate pieces of evidence that would lead to the explanation of the moving continents. The plate tectonics theory was born. At this time, scientists found out that the thermal convection is the driving force for the movement of the continents. The concept of thermal convection is based on the fact that as a substance is heated, its density decreases and rises to the surface until it is cooled and then sinks again. The repeating process of heating and cooling may produce a current that is strong enough to make the continents move. In later years, the concept of thermal convection was changed to mantle convection currents to specify that heat is actually radiating from the mantle. Now, the basis for the movement of continents progressed. Geologists started to use a more precise term to refer to the moving piece of crust as the plate, because it was believed that continents are not the only ones moving, as explained by Wegener. The boundaries of tectonic plates were accidentally discovered and eventually studied during magnetic surveys of the ocean floor and seismic activities for nuclear testing. We all know that lithosphere refers to the crust and the upper mantle of the Earth. It is made up of several tectonic plates that glide over the mantle. Tectonic plates are composed of oceanic lithosphere, the oceans and seas, and a thicker but less dense lithosphere, which is the land. After the plate boundaries were discovered, scientists were able to identify 8 major plates, and those are Pacific Plate, Indian Plate, Eurasian Plate, North American Plate, South American Plate, Indo-Australian Plate, Antarctic Plate, and African Plate, and several minor plates, one of which is the Philippine Plate. Actually, there are 3 major types of plate boundaries, and those are convergent, divergent, and transform boundary. The first one is convergent boundary, also known as the collisional boundary. It is where plates meet. This happens when two tectonic plates move toward each other brought by mantle convection, or the current convection from the heat of the mantle. Actually, there are 2 possible landforms can be created. One is trench and the other one is mountain. Trench is formed from subduction where denser plate sinks under the other or the less dense plate. Mountain formed neither plate is subducted but instead crumples into each other and somehow pushed upward or sideward. Convergent boundaries are where most of the destruction of crust takes place, specifically in the subduction zone. The next type is divergent boundary. It is where plates move away from each other. Plates move apart because of the magma that is being pushed upward in the boundaries of the plates. When this happens, the slowly moving plates transport newly formed crust away from the ridge as it spreads in both directions where the plates go. So this is how it looks like in divergent boundaries. The last type of plate boundary is what we call transform boundary. It is where plates slides past each other, meaning neither plates get subducted. Earthquakes are expected in transform boundaries because the type of stress present in rocks in this particular area is what we call shear stress. Frictions between the two sliding plates or rocks may cause a destructive phenomena, which is what we call earthquake. A perfect example of transform boundary is the San Andreas Fault, which is located between San Francisco and Los Angeles, California. Another example is the West Valley Fault, which is located here in the Philippines. Okay, so those are the different types of plate boundaries: the convergent, divergent, and transform boundary. At the boundaries of the tectonic plates are the areas where the highest hazards are. This is where the plates have the highest tension and therefore are exit points for energy release. Using the map, look for the Philippines. You will notice that the country lies on the boundaries of the Philippine plate. So what does this tell you? Being near or at the boundary of the Philippine plate make us prone to geohazards, especially when energy from the interior of the Earth exits through these boundaries. Aside from the shrinking and expansion of Earth's crust, deformation also happens during tectonic movement of the plates. Crustal deformation can either be folding or faulting. Okay, so there are two types of crustal movement, the folding and the faulting. Folding, also known as the horizontal movement of the Earth's crust. Geologic folding is a type of Earth movement resulting from the compression of rock strata or the rock layers. Bending, curving, crumpling, or buckling of rocks into folds is usually visible on the rock strata. An example of a landform created as a result of folding is the Himalayan mountains. There are three types of crustal folding. First one is the syncline, also known as the downward fold. The other one is anticline, also known as the upward fold. And the last one is what we call monocline, or also known as the slight fold. Folding can happen in oceans and seas. The compressional forces are strong enough to move ocean sediments to higher or lower elevations of folds. The area on higher elevations may eventually form land when solid particles build up on seabeds. The area on lower elevations may be filled with water from rivers and streams, thus forming a new type of body of water. The other type of crustal movement is what we call faulting. Faulting is also known as the vertical movement of the Earth's crust. It involves uplift or subsidence of crust along the lines of weakness. The cracks or fractures formed is called fault lines. Mountains are not just formed from folding. Faulting can also form mountains and valleys. Mountains are formed from faulting have sharp peaks, and they are called black mountains. The formation of a black mountain is caused by low temperatures, making rocks brittle. So instead of folding, rocks breaks into large chunks. On the other hand, valleys are formed from the displacement of rocks. So valleys are narrow depressions bounded by parallel faults. There are three types of crustal faulting. The first one, where the crust is being pulled apart, normal faulting occurs, in which the hanging wall block moves downward with respect to the footwall block. The other one is where the crust is being compressed. Reverse faulting occurs, in which the hanging wall block moves upward over the footwall block. Crustal blocks may also move sideways past each other, usually along the nearly vertical faults. This strike-slip movement is described as sinistral, when the far side moves to the left and when the far side moves to the right. Faults can be as short as a few meters and as long as 1,000 kilometers. The fault rupture from an earthquake isn't always a straight or continuous line. Sometimes, there can be short offsets between parts of the fault, and even major faults can have large bends in them. Okay, so those are the two types of crustal movement, the folding and the faulting. Always remember that separation must be done voluntarily by two equals. Alright, so that's all for this session. Thank you for listening and have a good day ahead.